Okay, today we're looking at fillet welds again, but now they're going to be in torsion or bending. We won't do both at the same time, not torsion and bending at the same time. We'll keep those separate, but they have a similar approach. And you'll see later there's some charts that we'll look at to help us solve these problems, and those charts work in a similar way. So let's just look through this. Let's see. This looks familiar. Very similar to what we did when we had bolts, except now these darker pink areas are welds instead of bolts. But you take a similar process that when you were using a bolt group as similar to what we're going to do with this weld group. There's going to be two shear components: a primary shear that is just a direct, the translational type shear, and then a torque related shear. Here they have a M for a moment, but it's going to be the same thing. So there's something that's called trying to rotate this part. So if we get this out of the way, I've got one drawn out here that we'll work on, but the direct shear is just trying to shear it directly down. In this case, we're pushing down on it. And then the secondary shear is there's some centroid in this weld group, and it's trying to twist it or rotate it around that centroid. And so we're going to do both of those just like we did with the bolt groups, and they will work in a similar way, except that there is a chart that will help us calculate some of the moments of inertia that we need. In the shear equals V over A. When we were talking about bolts, it was the area of the bolt. Here it's the area of the throat of the weld. So again, we're talking about that throat. Let's see if we can refresh what the throat means. So these are all fillet welds. So we do have that as a, constraint on what we're doing. But remember, we had a fillet weld that was basically a triangle. And so there's something welded together here. There's a piece here and a piece over here that are welded together somehow. And this is the weld. And the throat of the weld is this plane here that goes into the page. So it's tilted at a 45-degree angle here. We're also assuming these angles are 45 degrees, so it's just this leg and this leg are the same length on our welds. So that's the throat. We talked about that last time. And we're going to keep assuming that failure in these welds, these fillet welds, happens as a shear failure on that throat. So we're going to keep that as our area. Let's go back to here. Yeah, that's fine. What else do we have? We have this idea, so over here, so that would just be V over A. So the shear force, the direct shear force over that throat of the weld, all of it combined together, the whole weld group area, throat area combined together. Doesn't matter what angles or, horizontal or vertical or at some angle, it doesn't matter that. It's just all of that area added together. And then the secondary has this M or T, sometimes is listed in there. I think your book most of the time uses M. I think I'll have one where it's called T in a MathCAD sheet I worked out. But it's just the moment that's trying to, twist the part or rotate it. And then R is going to be some radial distance from the centroid to the point of interest. So we're going to pick on our weld group over here. I've got the green as the weld group. We're going to pick a point of interest just like we did with a bolt. It was more obvious when the bolts were there because there were, discrete bolts, whereas here we have this more continuous type thing. But basically, it's going to be one of the corners for our weld group, just like there was a bolt there. And we're going to pick one of those corners. And that R is going to be, we find the centroid of our weld group. So for this weld group, that centroid is going to be it's basically a letter C, and it's going to be somewhere over here. We'll actually have to find a real location for it, but somewhere over there. And R is going to be the distance from whatever point we're interested in. It might be that corner, and it's going to be the straight line between them. So that will be what I have as letter R in this equation. And then J, depending on if we're doing a bending or a torsional type setup, this would be the torsional. This would be the torsional setup. Bending would look more like this, where you have something sticking out, point load, and you're ripping it off of the wall, versus here it's flat against the wall. So torsion, bending, it's going to work the same way. The bending one, you would have an I in this equation, and torsional one, you'll have a J. So they're very similar. They're both moments of inertia, and they come from similar looking charts in your book. So you do have to be careful that you're using the right table. Table 9.1 for J and table 9.2 for I. So you do have to keep that straight. Here is a portion of table 9.1. And what you have in these tables, there's several pieces to it. So there's one part, there's other, here's 9.2 and another part of 9.2. So let's look at back to here. Actually, let's look at this one since it's the one that matches up with what we have here. So our weld group is this C shape. So in here, I'm looking for case number 4, which has a C shape pattern. And it gives me several different things here. It gives me the area. So this is the throat area of this weld all combined together. And you kind of can see it there because, let's make it a little bigger. So you can kind of see the 0.707H. That's going to be the 0.707 is the 45-degree angle to get the throat length. And then H is the weld size. So is it a 1/2-inch weld? It's probably not that big, but whatever size it is, a couple of millimeters, whatever units you're in. And then 2B plus D, there's B, B, and D. So it's just all of the total length of the weld. And so all of these have how you calculate the total area. They also have, if it's needed, like on the circle over here, they don't tell you how to find the centroid of the circle. They assume you know that. But even on ones that are just rectangles, they give you the equations for locating the centroid. Here, they give us the equation. Now, you do have to be careful sometimes because maybe the weld group that you have matches this pattern, but it's oriented differently. It's rotated 90 degrees, so you can't just automatically say, oh, X bar is whatever, and then assume that's in your X direction that's on your problem that you're working on. So you do have to line up what they have shown on here with the same directions that you have on your problem. Now, in our case, it does line up. The C is, looks like the letter C. It's not rotated any odd direction from that. And on our weld group, it's also letter C. Not stretched out, but that doesn't matter. That dimension will be taken into account in their variable B over here. And then over here, they have this. They don't have J. They have J sub U. So this is like a unit polar moment of inertia. So this will get you the polar moment of inertia. Now, there are techniques described in the chapter on how, if you have something other than a regular weld group, how to create that polar moment of inertia. Maybe you have welds that are different sizes. Maybe you have a 1/4-inch weld here and a 3/8-inch weld over here, and so you can't use this method from the chart when you have different weld sizes like that. But there is a method in the book outlined if for some reason you have different sizes of welds or something that's not in the charts. Here you can see we have a 0.25 inch fillet weld on the arrow side and the opposite side of wherever the arrow is pointing. Now, I pointed the arrow to the weld itself just because it was kind of cluttery to point to the edge of the part. But this weld call out is going to give us this weld, the 0.25 fillet on the arrow side, and then the other side of the arrow is this weld. So this one call out gives us this weld and this weld. It doesn't do this one though. This one has its own call out because I couldn't put the circle here doing all around because that would give me a weld back here also, which I didn't want. I just wanted the welds on here to have a C shape. So this one has a separate call out. Now I think I do have this triangle backwards. I don't know that it matters too much, but normally they're oriented this way, so I think that it should be a mirror image, but that's not a big deal for what we're doing anyway. And it's another 1/4 inch, so they're all the same size, fillet weld, and it's only on the arrow side of where it's pointing. So it should be pointing to this line. I just didn't draw it there because it got cluttery with everything on top of actually drawing the weld on the picture. Normally you don't draw the weld on the picture. So what this J will do, it will give us the polar moment of inertia for that weld, but it has nothing to, it doesn't know what size the weld is. So it makes it a unit polar moment of inertia. To get J, I need to multiply JU times the throat area. So 0.707, or well, the throat size, not the throat area. 0.707 times H. So if I take JU, multiply times 0.707 times H, the weld size, that will be the value that I'll use for J in my equations. Let's put this back to its regular position. And so you have all of these. You have, a straight line, parallel lines, an L shape, the C shape, rectangular shape, and a circular one. All of these are in table 9.1, and they are for torsion. You have very similar looking items. There's straight, parallel. They have parallel in 2 different orientations here. C, a C that's another direction, rectangle, and some T and I-beam looking weld groups, and a circle. These are, might have to zoom in to be able to see them. These are I. So these are when you have the bending set up. So don't just turn to one of these tables and use it without paying attention to what you've actually got going on, because it's really easy to just grab one of these tables and grab the wrong one and not get J when you need I, or I when you need J, or whatever, vice versa. So be careful that you're on the right table. They're on separate pages in your book. This is just reminders of things that we're going to assume. You should check for failure in the parent material and the weld. We're doing that through assuming there's mixing, so that we're going to assume that the weld becomes weaker, basically weak to the point of the parent material, which is not true. It's not going to come totally that weak, but there will be some areas that are mixed. The weld strength is dependent on the choice of the electrode material. We haven't looked at it a lot. Let me see if I have a chart of electrode strengths in here. Yes. So this is table 9.3. Here is a list of different electrodes from 60 to 120. And you can see they have different different strengths. And if you notice, the tensile strength for the 60 is 62 KSI, 70 is 70, and so forth. So they kind of line up. The 60 is more or less telling you the tensile strength. Then there's a yield strength and a percent elongation. So you do normally pick electrodes that are stronger than the parent material. That's what this is saying. But they do mix together and kind of make this odd area where you don't really know what's happening. The parent material experiences some form of heat treatment. It might be annealing or whatever. But it gets heated up, and so all that pre-stuff that you have done, maybe cold drawing it, work hardening it, a real heat treatment, that in that local area around the weld is, you're unsure about it. So you kind of have to go back to the hot rolled type properties for that parent material, and that's what this line says. A lot of times in this one, these joints are designed following codes, like the AISC code chart that we looked at earlier, this guy, where you just have a electrode material and linear feet of weld, and you can figure out how much force it can carry. So that happens similar, but again, remember, this chart doesn't assume any kind of mixing in the parent and weld material. So you do have to know that this is a less conservative approach than what we had been doing. Okay, so let's see how this works. So again, we're going to need at some point this, so we'll have to come back to that, but we don't need it right now. So here's our setup. We've got a 700, this is 700 if you can't read that, kind of close together. That's 700 pounds. We've got a beam cantilevered out here, not very far, 10 inches from this wall back on this side. It's welded to it in this C pattern. And the first thing we have to do is find the location of this centroid. Now, you can go in and treat these weld groups as rectangles and find their centroid that way. But for these that are in the chart, you do have equations already built out for finding the centroid. Now, in this case, we know that the centroid is, we know this distance. It's just going to be half of 1.5. So this is just going to be 0.75 inches. So we can do that one more by observation to find that location for the centroid. Might need a bigger marker. So that's 0.75. And I am going to put, here is X and Y. Although I think in their book, formulas, they're assuming this bottom left corner. Let's make that a lot bigger. They're assuming this bottom left corner is more or less the origin because they're measuring everything from that bottom left corner. That's fine. Let's see what they have for what is X bar. X bar does line up with this same distance here. I'll put it down here for now. And let's see, here it is, b squared over 2b plus d. Now you do have to be careful that maybe you've, like on my picture, I have labeled something here as d equals 2 inches, but if I look at their picture, they have d as a different measurement. What they have for what I labeled d equals 2 inches, they actually have that as the variable b. So don't just automatically go in and, oh, d is 2 inches or whatever. Make sure that what you're putting in here matches up with what the dimensions they're actually interested in are. So b is going to be, let's go back over here. X bar equals b squared over 2b plus d. And for them, b is this dimension, 2 inches, and d is this dimension, well, they have it labeled over here, but this dimension, 1.5 inches. So if I plug those in, got them over here in MathCAD. Well, I've already gone ahead and plugged in some things like F is 700 pounds, V is the same as F, so that's the shear force, that's the direct shear. There's the values for B and D. L is 10, that's kind of, let's see, remember that's this distance from the end to the wall portion. And then here's X bar. And it comes out that X bar is 0.727 inches. So something like that. And that is this distance. So now I've located the centroid. I know where the centroid is now. Let's draw, all right, it's getting really cluttery here. So let's take and simplify things. Let's just look at the weld group, and let's draw it bigger. So there's our weld group, not necessarily drawn to scale, but something like that. Our centroid is right in there. They label it G. That G is going to be in the way later, but that's fine. And then we had some dimensions on here that basically this is 0.727 inches. That's where we've gotten so far. Now we have to do a similar thing that we did last time with the bolts. Well, 2 times ago, whenever we did the bolts, where we need this 700 pounds applied at the centroid of our weld group. So to do that, we're just going to take 700 and move it over here. So let's do that. So that's the direct shear, the primary shear. And then this 700 pounds not only was trying to push or translate directly down, but it's also trying to rotate. And so I need to take that effect. What I've got here is just translation. There's no rotation caused by this 700 pounds about the centroid of this weld group. I need to create that rotation effect. So I'm going to put concentrated moment here that will simulate or recreate that rotational effect, that the 700 pounds at some distance. You know, this 700 pound has a moment arm of 10 plus whatever this distance is, 2 minus x bar. So I need to create that. So back in MathCAD, I calculated that. So here, this variable called arm is the moment arm. That's the distance from the point load 700 pounds, the original one, and the centroid of our weld group. So L is the 10 inches, B is 2 inches, minus x bar. So that should give us 10 plus 2 minus x bar gives us this moment arm, which is what I want. So turns out that that distance is 11.273 inches. The torque, or M, whichever letter you want to use, is that I need to apply at that weld group centroid to recreate the rotational effect is the F, 700 pounds times that moment arm, so 7,891 inch-pounds. I'm not going to put the decimals just because MathCAD can keep up with those, but it's cluttery on my picture. So 7, 8, 9, 1, those will be inch-pounds. So 7891 inch-pounds is there. Now these two represent that 1 point load that was off, off that way somewhere. And they create the same effect that that one 700 pound force did, except now they're applied at the centroid of our weld group. Now what we need to do is we can go in and calculate our primary shear. So primary shear is just the shear force over that total area. They give us in our chart over here, they give us a way to calculate the area. Right here's our weld group, here's area. So 0.707 H, we have H for our, well, it was on the order page. H for all of our welds is 1/4 inch, 0.25. So let's write that over here. Area is 0.707, so that's going to be getting the throat part, not just the leg. H is 1/4 inch. Multiply that times 2 times B. For us, B is, well, it's not labeled on this one, but it's the whole distance here. This is B equals 2 inches. So 2 inches plus D, this distance was D. And that was 1.5 inches. So plus 1.5 inches. So So our total area, if we look at MathCAD, I've built that equation. Area is 0.707 H, so that's the throat size, 2B plus D, 0.972 square inches. And primary shear stress is the shear force, which is 700 pounds, over the area, which we just found. So it turns out that primary shear stress is equal to 720. There's some decimals. I'm just going to leave it at 720 psi. Now this shear stress, so something that's a little different are bolts. You know, the bolts have split up the shear stress and everything, and we're trying to find how much force is applied to each bolt and everything. Here, we're just going to say that this shear stress exists on the whole weld group. So, you know, it's over here. This is my distributed shear stress. It's over here. I am drawing it. Notice the shear force is pointing down, and this is the stress that has to resist that force. Otherwise, you know, they're moving downwards. And I don't know how to draw it really well over here, but it's on this weld also. And anywhere I look, the stress, the primary shear stress, is 720 psi and some decimals. So this isn't, these aren't forces. There are forces associated with them, but this is actually stress, all on our weld group. Now, and that's the primary shear stress. So we know we at least have 720 psi, but we also have the secondary. So this is the one that's keeping, you know, from just sliding off the wall that we have it welded to. There's also the secondary that keeps it from staying in place, you know, as far as translation goes, but keeps it from rotating. So that's the secondary shear stress. So we have this type of equation. Let's put it down here. And you, again, I think in the beginning in the PowerPoint, I had it as a M. Sometimes you'll see it as a T times R over J. There we go. T times R over J. So T is the torque, the 7,891 inch-pounds. That exists everywhere. That's just the applied torque to the weld group. So that's a static number that's going to be, no matter what point I choose, normally you're choosing endpoints like this point, that corner, or that endpoint as your point of interest. That's usually where the worst of the shear is going to be and the failure would begin. So I'm going to choose one of those points. And J also is a property of the whole weld group. So T and J, no matter what point I choose, they're the same numbers. T is 7,891 inch-pounds. J, we haven't found yet. We need to go and calculate J. So there's the JU. And I do have that built into MathCAD right here. Right, this equation, JU. And so I get a number for JU. Notice it's in inches cubed, and moments of inertia are in length to the fourth power. So this does say that I'm missing something. So that'll give you a clue also if you forget to multiply JU times the weld throat size, then your units won't work out because you'll have inches cubed in the denominator. And if you're tracking your units, which you should be doing, then your units will be some odd thing that doesn't make sense. So JU does come out in inches cubed. To get it over to inches to the fourth power, you got to multiply JU right here times H, the weld size, so that's the 0.25 inches for us. That's where the other inches come in also to get to inches to the fourth. And then 0.707 because we want to calculate the throat size, not the leg size of the weld. And so J, the number that goes in our equation, is actually 0.876 inches to the fourth. Okay, that leaves us, let's get some of this stuff off the screen. That leaves us, T is 7,891 inch-pounds. Oh, I have to slide over. R, we don't know. J is 0.876 inches to the fourth. Okay, so R is the only thing that changes depending on my location from the centroid. And remember that R is from the centroid to whatever point I'm interested in. So technically I could go, to any point in the weld group, but I probably want to know where the worst case shear stress is, which means if R is in the numerator, what's the biggest value I can put for R into this equation? And if you draw this relatively to scale, which is, ours is close, I didn't measure anything, but it's close to scale, then it's pretty easy to see that the largest line that I could draw from the centroid to any point on the weld is either this line or, this one would be the same line also. So either one of those. I'll just do this one. So if I think about this point, then this shear stress is going to be at a right angle to this moment arm. So it's going to come out, I don't know, something like this. Something like that. And where this is a right angle. And I can calculate that. If I think about, let's just draw another one just so we make sure we know. Let's do this one over here as an example. So here would be another R that I could put into my equation. This distance, obviously, again, if this is drawn to scale, this distance is a smaller distance than that one, which would generate a smaller secondary shear stress. Also, this number coming off of here is so it's a smaller magnitude just because there's a smaller number R, but it is competing with this. They don't add together. So remember, this is our primary shear pointing upwards. Here, now how you pick the direction for, I guess I didn't actually explain how you know which way this one's going, but it's resisting this moment. So I've got a clockwise moment here, so I have to create a counterclockwise moment here, just like we did with the bolt groups. So clockwise moment or clockwise torque applied to the centroid, I'm going to resist that with a counterclockwise torque. Now this is actually showing a shear stress, but there's a torque associated with it right here, and it has to resist it. So no matter where you draw the arrow for the secondary shear stress has to create a torque that's going to oppose the applied torque so that you have equilibrium. And so at this point over here in weld group, and again, normally you're looking at corners and endpoints as your potential failure points. Almost treat it like a bolt group, and with bolts at every one of those corners. And here I've got a positive Y on my primary shear and a negative Y on the secondary shear. So they're going to subtract each other. Here I've got a positive Y on my primary, a positive Y on the secondary. So they're adding, and then I've got a negative X, but I have no X at all on the primary one. So again, that is going to add together because there's nothing else to oppose it. I don't have any primary shear going out that way. So this is the point that I think this or this, because this one, might as well make it really cluttery. So this one, this R are the same, you know, just from geometry. We haven't found their value yet, but we know they're the same. And then stress would come out here. And positive Y components on the primary and secondary, so they're add just like this one. The only difference here is I have a positive X and a 0X on the primary shear, so they would create the same effect. So either this or this are going to have the same total shear stress on them, and so they're going to be equally bad points to deal with. All right, so let's just look at this one. This one and this point are going to have the same magnitude when we're done with them, so we'll just pick one of them. So R, we need to find R. That's the length of this line. So if we look at it as a triangle, this distance is, we don't really know. I had it in MathCAD, but let's just do it real quick. That whole base was 2 minus this distance is 0.727. So this is 1.273 inches. This distance is half of D, so that's 0.75. So now I've got a right triangle. This is the hypotenuse of it, and I can just easily solve for that distance, which I did. Let's see. I built it as rise over run. I did that for a reason in a second that I'll show you, but rise over run, there's the same numbers that we just used. Square root of the summation of squares gives me R is 1.48. So that would be the R that goes into this equation. Once I put R in there, I have a value for the secondary shear, and it is, oh, let's keep it with blue since everything else was blue. 13,300 and we'll call it 9 psi. So pretty big number compared to the primary, which was 720 psi. Okay, but I don't just add tau prime to tau double prime. Can't just add them together because they're not totally adding together. They're not in the same direction. So I have to add the Y components together and I have to add the X components together. So I do have to do that. And that's why I put, in MathCAD, that's why I put rise and run in here. So remember that, you know, this is rise and this is run. And if I want a perpendicular line to this one, which I want this secondary shear stress, let's make it a little bigger, longer rather. If I want it to be perpendicular, an easy way to do that is to take the rise of the blue line and make that the run of the red line. So make this 0.75 and make, same thing with the run of the blue line, I make that the rise of the red line, 1.273. So now by inverting the rise and run from blue to red, I know that blue and red are perpendicular, just from geometry or whatever that is, that stuff. All right, so that's why in MathCAD I labeled them as rise and run. So here we have the secondary shear calculation, and here we're calculating X and Y components. So the X component is the secondary shear force times the rise, because we're actually doing, that's the 0.75 number, rise is 0.75, over R, which is the hypotenuse. And so we get 6,700, 6,800 psi for the X component of the secondary shear. The Y component, and there's no X component of the primary shear. The primary shear is only in the Y direction, so it has no X component. I think your book might actually have an equation that shows how to combine these together, but it doesn't necessarily explain why sometimes you have an X component in one and not in the other. And I can't remember if that's in this book or another book, but sometimes that's confusing. Just think of it as you're finding the X and Y components of the primary and secondary and adding them together. So only the secondary has an X component in our scenario right here. They both have Y components, so here is the Y component. Again, this is run, which is the 1.273 number over R. And if you look, that would be 1.273 over R, which would give me the Y component. I'm assuming Y is positive when it goes up. And there is a primary. This is what I have for the primary. This is a 720 psi. You add all that together and you get 12,000 psi. Now you can add the X and Y components together in the normal way. The summation of the square root of the summation of the squares of the X and Y components, and you get a total of 13,900 psi of shear stress. We don't have to call it primary or secondary or anything. It's just shear stress at that corner that we were interested in, at that corner. And by symmetry, we know that there's also that much shear stress at this corner. We don't know about these corners. We didn't calculate those. We do know that they are smaller values because tau prime itself is smaller, and when you go to add the Y components, you're going to have positive Y here and negative Y on this one, and you'll have the same thing up here. And so we know that they are worst case scenarios, and we don't have to worry about, or at least in this case we don't, and you normally don't have to worry about this, the weld changing size. So normally you do have the same size weld all the way around. Whereas with the bolts, remember we had a bolt pattern where there was a larger bolt and two smaller bolts, and we did have to worry about the smaller bolts. You don't really have to worry about that thing in this weld setup. All right, so that is the torsional one. All right, bending is going to be like this. I don't know what that is. So here we've got a now these just doesn't have variable set. It just has variable defined, but no actual numbers here. So we have a fillet weld, and this one is all the way around. So it's all the way around this cylinder. The cylinder's some length L. It has an outer diameter D and some force point load applied to the end of it. So this is not creating a setup where we have the torsion. This is the bending setup. So this is, it's trying to be bent. I can't really do it in 3D, but it's bent off the wall. The top here is pulling away from the wall. The bottom's actually pushing into the wall. So there's a bending stress that wants to happen here. So to do this, you would need the other set of charts for I. And if we go to the very bottom, down here, let's get that one out of the way and just look at I. I didn't want to stretch it out. So circle, it gives you the total weld area, and it gives you pi r cubed for the moment of inertia, for the unit moment of inertia. Again, this is IU, not I, but it works the same way. So when you're solving this guy, it looks very similar, where you have primary shear equals V over A. Now I haven't already solved this one, so we might have to calculate some things, but it's not much to calculate. V is the shear force F. I don't know what let's just give that 1,000 pounds. So we're saying the F is 1,000 pounds. Over A, we have to look back here. It says that A, the area of the throat of the weld for a circle of some radius, is 1.414 times pi times H, our weld size. We didn't give it a weld size. Let's say that H is a, let's do a small weld. Oh, no, let's do a 1/4 inch again. So 0.25. And then times R, which we don't know. But we know the diameter D is 2 inches. So that makes R 1 inch. So this, we don't know, let's see. We have 1,000 pounds of shear force divided by 1.414 divided by pi divided by 0.25 divided by 1. So we have 900.45 PSI, pounds per square inch. There should be an inch on that one also, of direct shear. And so this is the shear that is, you know, straight here on the weld, all the way around. Okay. And then we have the moment. I'm just looking up something in the book. We have the tau double prime equals, here maybe we'll use the M. This looks more like a moment to me, where the other one looked more like a torque. So it doesn't matter. This is the same units and everything. So whatever you want to use. M, I think your book uses R again. That might get confusing because we already have an R, although in this case the R is what we need. So we'll leave it over I. You might have seen this equation MC over I before for a bending type stress. Although we are in a shear stress, though. We are assuming this is shear stress. All right. So M, we need to figure that out. M is the bending moment applied when I push over here. So F times L will give me the bending moment back at the wall. So I need a value for L. Let's just make it similar to the other one where it's 10 inches again. So that gives us 1,000 pounds times 10-inch moment arm. Gives us 10,000 inch-pounds for M. R is, so back here at the wall, you know, I've got some axis that I'm trying to draw through the, you know, this axis is basically on the plane of the wall, and R is going to be the distance from that centroid. The centroid for my circle back here, you know, is right there in the center. Make it a little bigger. So R is the distance from that centroid to the point of interest. My point of interest, I didn't point it out, I guess, is right up here on top. That's where I believe that the worst case would be. If I'm pushing down here, there's a good chance that it could pull away from the wall at the top. On the bottom, it actually could still break the weld, but if it did, then it's going to push it into the wall, and you know, it would still hang on there, assuming there's some weld at the top still. So, and that would give me the same exact numbers that I'm going to calculate here anyway. So distance from here to the top of the weld is my radius, which diameter of 2 inches, so radius is 1 inch, over I. So I, we got to go back and look up. I is over here. I'll just zoom in so I can see it. IU equals pi r cubed. That's it. So IU equals pi r cubed. Now, r for us is the radius of that. This radius, r, is talking about the radius of the circle. So we have the radius set at 1. So this is just pi. But that's IU, and it's pi inches cubed. Over here I need I, so you do that the same way that you did before. I equals 0.707 times our weld size H, so which is 0.25. It's off the top of your screen, right there. So this gets the throat times that unit moment of inertia, which was just pi inches cubed. All right. So I turns out to be 0.707 times 0.25 times pi. 0.555. We'll do 555 inches to the fourth. And put that in here. And we can calculate our secondary shear stress. 10,000 pounds times 1 divided by 0.555. 18,018 psi. Now these we combine together. We don't have to worry about some off-angle shear stress. I'm not sure if I can draw this one very well, but the secondary is, it's right here. So these are the primary. This is the secondary, and all you have to do, so the secondary is right in there, right there, is use summation or square root of the summation of tau prime squared plus tau double prime squared. So that would look like this. Our shear stress tau equals square root of our primary squared plus our secondary. They're already at right angles to one another, squared. Our primary was 900 psi squared, plus our secondary was 1818 psi squared, and that gives us, 900 squared plus 18018 squared. Take the square root. Where did square root go? There it is. Of that answer, 1840. 18,040 psi. And so that would be the shear stress, the total shear stress at that point up there that we'd have to guard against. Now those numbers are getting really close to, if we were using that E60, the allowable shear stress in that is maybe smaller than, it might be around 16,000 psi. I don't remember offhand. We're not actually doing any designing, we're just doing analysis right now. But you could take and check that out. And that doesn't include any mixing that might have come from whatever parent material we had back here, and whatever this thing was made of. So we were getting close to probably some dangerous situations with these welds that we designed or analyzed today. We didn't design them. They were already set in their dimensions. Okay, that should do it for welds in torsion and welds in bending. Very similar processes. You do have to make sure that you're using the correct table. JU for the torsion, I and IU for the bending. And then next time we will look at, actually next time we'll have an exam, but the next time we talk, it will be fatigue. So welds in fatigue. So we have some kind of repeating loads applied to these welds, and we'll deal with that. Okay, I think that should do it for today. Bye.